Hello everyone. So for this video, I want to go over section 2.4, the product and quotient rule. And this is just another tool to add to your toolbox of derivatives. And I'm going to show you the basic rules for product rule and quotient rule. And we're just going to do some practice problems and we're going to call it a day. So for this one, I think I'm going to be okay for now with you guys just leaving everything in an unsimplified form, because you'll soon find out that, like, in order to simplify some of these derivatives, it's gonna be very lengthy if you end up doing it. So for right now, I'm okay if you leave all of your answers like in an unsimplified version, kind of like in the past, but just know that there might be a multiple choice question where the answer choice is going to show it simplified, and you have to recognize which one is equivalent to the derivative that you worked out. So let's just go ahead and start with the product rule. It's very simple. All you got to think about is if you have the derivative, right, of two different functions, or like two different expressions that are being multiplied to each other, then all you have to do is do the first expression times the derivative of the second plus the second expression times the derivative of the first expression. All right. And if you ever see me in class or even throughout this video, I'm always going to repeat it. First times the derivative of the second plus the second times the derivative of the first. Okay. So really the hard part with this is just kind of identifying which two things you're going to, which two expressions you notice are being multiplied to each other, and then like separating them out like that. All right. So, I mean, some people like to actually write it out at the corner of their paper, F, G, G, F, with a plus, and then put the tick mark on the second ones. So to remember the first times the derivative of the second, plus the second times the derivative of the first. So I guess to do a few examples, what I'll probably do A, because that's a pretty simplistic example, maybe B, and I'll do G and H. And then the rest of them, I'll just post the solutions online. So for A, let's just kind of start off simple. So you notice here that you have two different expressions being multiplied to each other. So I'm going to think of this as F, and I'm going to think of this as G, right? So the derivative of the whole thing, right? Maybe I shouldn't use F because the whole thing is F of F. Whatever, we'll just go with it. So it's the first expression times the derivative of the second expression, which the derivative of this is just going to be 1 minus 0. So we'll just say 1. Plus the second expression times the derivative of the first expression. So derivative of that will be 2 minus 0, so we'll just say 2. Now I'm going to go ahead and simplify this one because it's pretty simple enough. You know, you could just say that that's 2x minus 1 plus, and then if I distribute the 2, plus 2x minus 8. And then if I combine my like terms, I have 4x, and then negative 1 and negative 8 is minus 9. All right. So sometimes you'll see me simplify it. Other times, like with part B, I'm not even going to bother simplifying it because I'm going to end up doing a whole bunch of distributive property and a whole bunch of foiling, as some of you like to call it, and it's just going to get ugly and messy, and I'm probably going to mess up the algebra somewhere, so I'm not going to even bother. But I'll show you, but we'll do the derivative. So the y prime, so again, this is like expression 1, so I'll call this F, and expression 2. I'll call this G, right? So the first times the derivative of the second, so the first is just x squared plus 3x minus 1, times the derivative of the second is going to be, if I do power rule, is 4x, plus the second, 2x squared minus 5. I'm running out of space here, so I'll just kind of continue it down here, times the derivative of the second. Or no, the second times the derivative of the first. So the derivative of the first is just 2x plus 3. All right. Sure, if I want, I can distribute this and foil all of that and then combine my like terms at the end. But I'm just going to leave it like that for now because this is technically the correct answer. And on the AP exam, especially in the free response, they're just testing your calculus skills, not so much your algebra. So if you screw up the algebra, then you'll probably get some points off, and we don't want that to happen. And a lot of times what they would probably do is have you plug in an x value, which you can plug in an x value directly into this. You don't have to simplify it first. So just a few things to keep in mind. So let's get into some of the more complicated ones. So again, I have this expression here and that expression there. So we have two different types of derivatives, right? We have the derivative of e to the u times u prime, and then over here we have a chain rule that we have to apply within the product rule. So you'll notice that the more rules we learn, the more complicated the problems can get because you're utilizing many different tools to answer just one derivative. So we'll just kind of, but ultimately we're still doing the product rule above everything. So we're going to do y prime. So we have this expression and this expression. So the first times the derivative of the second, which again, the derivative of e is just e to the u, times u prime. So the u prime is the derivative of the exponent, so that's just 6x, plus the second, e to the 3x squared, I'm going to put that in parentheses, times the derivative of the first. So the first times the derivative of the second, plus the second times the derivative of the first. So this one we got to use chain rule. So we got to bring the 4 over to the front. So actually I'm going to put 4 there. And then keep the inside, subtract 1 from the exponent, and then multiply again by the derivative of the inside. All right. So as you can see, these can get pretty long and complicated once you do the product rule. But if you look at like each piece separately, it's really not all that bad. All right, and again, I'm okay if you leave the answer like that, right? Sure, we can multiply the 3 and the 4 and combine them together and make it look a little nicer. But for right now, I'm pretty sure later on when you do some more derivative problems or they ask you to do related rates, they're just going to ask you to plug in an x value into this and then figure something out. They're not going to expect you to have a simplified version. However, and I'll say it again, I know I sound like a broken record here, but if this is on a multiple choice exam, maybe it'll show it all worked out like this. Maybe they'll combine like terms and multiply things out. Who knows? So let's do a we'll see how the product rule can be used with trigonometry. So again, I have two the hard part here is recognizing that there are two different expressions being multiplied to each other. So here I'll call this the first expression. I'll call this the second expression. So then the derivative of the whole thing is first, just as is, times the derivative of the second. So the derivative of cosine is negative sine of whatever I have inside, and then multiplied by the derivative of the inside. So the derivative of the inside is 5x to the fourth, plus the second times the derivative of the first. So I'll just leave this as cosine of x to the fifth. So the second as is, times the derivative of the first. So that's just secant squared of 3x. But in order to take the derivative of this, you have to also multiply by the derivative of the inside. So times 3, right? So again, if I took the derivative of tangent on its own without the cosine there, I would end up with secant squared of the inside times the derivative of the inside. Okay, so don't forget to do that extra step of taking the full derivative of whatever expression you're looking at. All right, so I think that's enough examples for the product rule. I think we should just sort of, I'm going to, for these 4 in the middle, I'll send you guys the solutions on Canvas. I know I've been a little bit bad about that, but I'll try to get my act together today being Monday. So, all right, now let's do the quotient rule. Oh, I didn't realize my pen would bleed through, but anyways. So the quotient rule is pretty similar. It's a little bit more complicated. If I took the derivative, right, quotient being fraction, right? So if I have the derivative of a fraction of expression, so if I have like an expression on the numerator and then an expression on the denominator, it's simply going to be the bottom times the derivative of the top, okay, minus the top times the derivative of the bottom over the bottom squared. Okay? And you'll hear me say the same phrasing. Every time I do problems, I say the phrase bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. There are a few mnemonics you can use here. The most popular one that you'll see like every single college student use or even AP Calculus student use is low D high minus high D low over low squared. So this is just telling you like get the low part of the fraction times the derivative of the high part of the fraction minus the high part of the fraction times the derivative of the low part of the fraction divided by low squared. So, and again, it's a very easy phrase to remember. Low d high minus high d low over low squared. So if you just say that like 10 times to yourself, and you'll remember this phrase, and then every time you realize you're going to have to do the quotient rule, just write this on the corner of your paper, and it's a really good reminder, and you can just kind of refer to it. In fact, for these examples, I'll go ahead and refer to that. So I'll do, I guess I'll do A and C, just to do a couple of examples for you guys. All right, so again, I have my low part of the fraction and my high part of the fraction. So obviously I'm going to use quotient rule because I see a fraction of expressions. So if I took the derivative of this, it's going to be low, so just the low as is, d high, so the derivative of the high part. So the derivative of this is going to be 6x squared plus 8x. Okay, so low d high minus high. So I'm going to oh man, I ran out of space. Oh, well, I'll just write over here because I'm not going to do this problem anyways. Minus high 2x cubed plus 4x squared minus 7. D low, so the derivative of the low is just 1, all divided by the bottom squared, or low squared. So x minus 5 squared. Some people say low, which, whatever, it's kind of a weird way of saying it. But anyways, so again, just like I said from the front page, I'm fine if you just leave it in this form, okay? Even on the test, I'm okay if you leave it like this, all right? Again, but bear in mind that there might be a multiple choice question. All right, so then again, I'm just gonna do the same thing for part C. I have the low part of the fraction, I have the high part of the fraction. So the derivative is equal to low, d high, the derivative of natural log is derivative of the inside over the inside, u prime over u, so 1 over x, minus high, natural log of x, times the derivative of that is going to be just 1 all over the bottom squared. That's it. All right. They will get complicated sometimes. And then for this part, I just thought this was kind of neat. You know how, like, for the derivative of cosecant, you should have memorized it by now, is going to be negative cosecant theta, negative cosecant theta. Oh my God, I already forgot. Cotangent theta, sorry. So it's negative cosecant, cotangent. So again, you can actually prove all of these using the quotient rule. So I'll just do A and C, and then you prove the next two. So for this one, if I did it, it would be, again, you have to know some of your identities. So the identity for cosecant is 1 over sine of theta, right? So if I did the quotient rule with this, well, I have f prime of theta is equal to the low d high, the derivative of a constant is 0, minus high times the derivative of low, so d low is negative cosine of theta. No, positive, sorry. Derivative sign is positive cosine. I'm out of practice myself. And then times the bottom squared, so sine squared of theta. Some background noise. Okay, so obviously this is going to be 0. And so you can almost think of this, and I'm going to kind of break it up as if like negative 1 over sine of theta times cosine over sine of theta. Cosine of theta over sine of theta, right? Because again, I'm just breaking up the denominator into, because if I multiplied across, I would end up with sine squared. And then you'll notice here that 1 over sine is negative cosecant of theta. Oh my God, what is with my handwriting today? Negative cosecant theta, and then cosine over sine is cotangent of theta, right? Which, again, isn't that the rule? The derivative of cosecant theta is negative cosecant theta, cotangent theta. So, I mean, in case you ever forget, I don't recommend doing this every time I just think you should just remember it. But it's kind of cool to see that proof. And you can kind of do the same thing with tangent. If you remember, tangent, the derivative of tangent theta was secant squared theta, but we'll kind of see for ourselves. Tangent theta is sine of theta over cosine of theta, right? So if I have a quotient, so I can go ahead and do the quotient rule. And if I do the low cosine theta times d high, so that's negative, no, why do I keep saying negative? Wait, yeah, no. Derivative of sine is cosine of theta minus high d low, so sine of theta, times the derivative of cosine is negative sine of theta, all over cosine. Cosine squared of theta, I'm just gonna separate it out already as this, just so that you guys can see it. Kind of skip a step. So then this becomes cosine squared of theta plus, because the two negatives, plus sine squared of theta over cosine of theta. Actually, I could just say whatever. That was dumb. Anyway, so then if you remember the one trigonometric identity, sine squared plus cosine squared is 1. And I should have just left it as cosine squared of theta in hindsight, but whatever, that's fine. So 1 over cosine squared of theta, and 1 over cosine is going to be secant, right? So 1 over cosine squared is just going to be secant squared of theta. And that makes sense. The derivative of tangent is secant squared of theta. All right, I thought I was being clever by keeping it separate, but I ended up just combining them at the end. So that's pretty much all you need to know for the quotient and product rule. And just like with everything else, it's only a matter, you're only going to get as good as the amount you practice. So try to practice as many problems as you can. I did put, for this section, I don't remember how many problems I put, but I think I put quite a few for you guys to get good at this. And again, just another tool in your toolbox, and this is going to be really helpful for later. So if you have any questions, just let me know, and I'll try to help you as best as I can. Take care.